So yeah, a little bit about adhesion. Trying not to choose the squeaky pens, but somehow all pens will squeak. Yeah, so this is a topic I remember when I was doing chemistry all those years ago, that I found a little bit tricky to understand. Not so much the adhesion thing, it was more to do with what we call polarity. What does polarity mean? I have given a talk about the water molecule, which, if you remember, is this bent shape, which is actually quite amazingly important, actually. The hydrogen atoms, because the nucleus of the hydrogen atom only has one proton, which is one positive charge, compared with the oxygen atom, which has considerably more. It has 6 protons, I believe. You better look that up. Might be 8, actually, come to think of it. Oxygen 16. Come on, let's do some chemistry. 16, so it must have 8 protons, mustn't it? 8 protons and 8 neutrons. 8 protons, 8 neutrons. The reason I was thinking 6 is because oxygen's in group 6 of the periodic table. The important thing is that we've got 8 protons in the oxygen nucleus and 1 proton in the hydrogen nucleus, so there is a tendency for electron density to be pulled in a bond towards the oxygen atom. The oxygen atom, as a consequence, acquires a slightly negative charge, which we put a little symbol delta, and the hydrogen atom, as a consequence, has a slightly positive charge. Yeah, that should be 2 delta, but forget about that. We're not doing maths, we're doing chemistry. Slightly negative charge on the oxygen, slightly positive charge on the hydrogen. The net result, we often draw a symbol that looks like this, where we have an arrow with a little plus sign at the bottom. The positive end of the molecule is here, and the negative end of the molecule is here. That is called a dipole, because there are 2 poles. Sorry about the squeaky pen. A dipole is called a dipole because there are 2 poles. Quite simple. If you think about the planet Earth, that has a north pole and a south pole, that also is a dipole, but it's a magnetic dipole. This is an electric dipole. Positive end, negative end, and of course negative attracts positive, so what happens is that water molecules tend to want to cluster. So the hydrogen, the positive end of a water molecule, is attracted to the negative end, the oxygen, of another adjacent water molecule. That is actually quite a strong bond. That's called a hydrogen bond. It's actually pretty strong. It's not as strong as a covalent bond, which is the type of bond that links oxygen to hydrogen, but it is pretty strong, about a quarter of the bond strength. And that means that water molecules tend to want to form clusters, and because they want to form clusters, water is a liquid at room temperature, which is obvious to us. Of course it's a liquid, but actually it shouldn't be, because if you think about something that's much heavier than water, hydrogen sulfide, where the oxygen's been replaced by sulfur, H2S, very stinky stuff, that's a gas at room temperature. So really, water ought to be a gas. It's made from 2 gases. And the reason it isn't is because of this hydrogen bonding. So that's actually quite an important property for the existence of life, really. So it's got a dipole. These dipoles attract each other. Of course, these clusters form and break because there's a lot of thermal energy in water. So these things are constantly breaking, reforming. In ice, of course, the bonds become, or the structures become frozen, more permanent, but ice is the solid form of water. And it has a very high melting point compared with many other compounds because of this property of it being dipole. We call these types of molecules polar, and we call the property polarity. And that's really important because if you don't have these dipoles in a molecule, high hydroxyl groups are really important, as you'll probably remember from some of the other talks I gave about wood. A lot of the structure of wood is controlled by these hydrogen bonds with the hydroxyl groups, particularly in the cellulose microfibril. If you don't have this, you only have these van der Waals forces, which are very weak, and they're what are called instantaneous dipoles. So things like hydrocarbons have very low boiling points. They tend to be quite gaseous or very volatile because the interaction between the molecules is much, much weaker. And molecules of that type are said to be non-polar. And basically the two don't mix. It's the old oil and water thing. Oil doesn't mix with water. Oil is non-polar, water is polar, and the two aren't compatible. I've talked about this, I think, when I was talking about microfibrils in lignin. It's the same kind of issue, because lignin doesn't have many hydroxyl groups. It's essentially a non-polar molecule, whereas cellulose, hemicellulose, these are polar molecules, and they're not actually very compatible. I think that's all I've got room for on this board to say. I talk about this now. You won't see it, but there's going to be a frantic cleaning exercise going on.